Can you believe there was a time when deep neural network was considered useless? I mean, the very technology that powers ChatGPT. Let's look at the 7 key breakthroughs that had to happen before today's AI could speak, generate images, and reason. On October 11, 1999, Nvidia released the GeForce 256 and coined the term graphics processing unit. It was built for the heavy linear algebra in video games, and no one thought of using it for machine learning. But this single piece of technology would later be the bedrock of modern AI, where 7 other core breakthroughs would have to sit on to make ChatGPT a possibility. By this time, serious work on large language models had already started. Back in 1986, deep neural networks were introduced by stacking multiple layers of neurons. It was considered impractical because the signal to correct the weight of the model during training kept getting out of hand or completely insignificant before reaching the very end of the network. This was called the vanishing and exploding gradient problem, and it meant deeper nets didn't actually learn better than shallow ones. Also, training even a few layers on CPUs was slow and could easily take weeks or months. And also, deep neural network only really shine when trained on large labeled datasets, which were not available at that time. In 2006, Geoffrey Hinton, which later became a Nobel Prize laureate and godfather of AI, revived deep learning with 2 landmark papers. His team proposed training each layer separately before fine-tuning the full stack. This solved the gradient issues, sparking new interest in deep nets. But large data and compute were still big problems. And in 2009, Professor Fei-Fei Li and some PhD students at Stanford compiled the ImageNet dataset, which consisted 3.2 million labeled images, and this provided the needed data for deep learning. So in 2012, Hinton, Alex, and Ilya built AlexNet, trained on ImageNet datasets using 2 Nvidia GPUs. That same year, it won the ImageNet challenge with a 15.3% error rate, crushing older methods stuck above 26%. This showed the real power of deep nets. I would like to mention that what surprised me is that it took them 6 years before realizing that they could use GPU instead of CPU for the training, and so I dug deeper to find out how they came across this idea. Well, it turns out that all this time, GPUs were not general purpose until the release of CUDA in 2007, which made it possible to run any parallel process on GPUs apart from graphics. From there, people started trying it out with different things like molecular dynamics, physics simulation, and of course, machine learning. All the progress earlier were in image processing, though the concept of deep neural network using large datasets and using GPU were transferable to NLP, which was kind of lagging behind. And by this time, Google Translate was struggling because words were just arbitrary numbers. So they introduced word2vec, which represented words as vectors. Suddenly, we can do something like king minus man plus woman equals to queen. This implied that the primary job of a model would be to learn these vector representations from large data corpora. Even with this progress, translation required full sentence context. So Google built Seq2Seq, which could read entire sequences, but with long sentences, it lost track. So the attention mechanism was introduced, letting words check back for meaning and context. By 2015, deep nets were popular in NLP, but training corrections were inefficient. Yeah, every layer got the same adjustment, so the Adam Optimizer was introduced. This optimizer scaled corrections per layer, and the residual connection was also introduced to ensure corrections reached the exact layer that needed them. By 2017, the combination of the Seq2Seq model with the attention mechanism was working well for Google Translate, but training took forever because it was built on recurrent neural networks. which processed tokens sequentially. Their solution was redesign the model from scratch, leading to the development of the transformer architecture in the now famous paper Attention is All You Need. This new design leveraged the parallel processing ability of GPUs to handle all tokens in a sequence simultaneously, resulting in a massive improvement in both training and inference time. It also introduced self-attention instead of recurrence, ensuring that no matter the length of the sequence, context wasn't lost. After the introduction of the transformer, several experiments by Google and OpenAI revealed the scaling law, which proposed that a model's performance would improve consistently as both the number of parameters and the amount of training data increased. So in 2020, OpenAI decided to push the transformer to its limit with a whopping 175 billion parameters and trained it on nearly the whole internet's data. This was the first time the term large language model was introduced and became mainstream. And later in 2022, they made it available for public use and it took the world by storm, reaching 1 million users in 5 days and 100 million active users in just 2 months, which was a record at that time.